Welcome back, everyone, to the Algebraic Graph Theory Seminar. This week we have Lavanya Selvaganesh, and she'll be talking about spectral properties of eccentricity matrix for special classes of graphs.
Thank you, Sabrina. I hope I'm audible. Yeah, so today, being the last seminar of this session, I wouldn't take it not too deep, but we'll try to discuss something about elementary topic on eccentricity matrix. And of course, this is completely away from the quantum results that we've been seeing in this seminar series. Okay, but I do have some interest if anybody would be interested to apply the quantum techniques with this matrix. I would also like to try it out. Okay, so I'm giving a heads up information for all. So let me just go with the outline. So today's talk is going to be on we'll introduce what is an eccentricity matrix. And then I want to talk about some matrix properties of this, especially the irreducibility and the spectral aspects of this matrix. And one other class of graphs, and which was interesting to me at least, to study the spectral properties. So we'll discuss about the windmill graphs and Dutch windmill graphs, which I think I had been hearing this word since like last 1 or 2 months at least after, if I'm not wrong, sorry, I don't know the name. She introduced to me this terminology of Dutch windmill graphs. So let me also thank that speaker on that day. She introduced to me this terminology. We knew it as friendship graph and other names are there for this. So we'll also talk about some eccentricity spectrum of this particular collection of graphs. So eccentricity matrix, it is defined using the distance matrix. So any ijth entry in the matrix is going to be nothing but if the distance between the I and jth entry, that is the ith vertex and the jth vertex, is equal to the eccentricity of the matrix, then we take the entry to be the distance itself, or it is considered to be 0. So this is informally, I've just defined it. So this was introduced first by Randic in around 2010, I guess. So observed that this matrix might open new directions, especially in chemical graph theory, where they were trying to discuss about certain properties from the mathematical chemistry perspective. And also, of course, in graph theory itself, it has a good role because of the role of eccentricity in graphs. And one more thing, if we see this matrix, this is kind of an opposite to the adjacency matrix. Okay, like if we know the adjacency matrix is based on the distance 1 entry, right? Whereas this matrix contains entries only at those points where the eccentricity is attained, or the pairs of vertices which are farthest. Okay, so that is one interesting property here that we have. And this property was again like further, this matrix was studied by Wang and others, and recently they started studying this matrix in 2016, 16 or 13, sorry, 18, and it came back again, and there are lots of other studies also that are going on, especially in the spectral properties of this matrix are being explored. So now, so as I was saying, they are like, if you look at the distance matrix, adjacency matrix takes those entries where the distance is minimum between any two pairs of vertices, whereas eccentricity matrix takes distance where any two vertices have farthest distance. So they are like kind of two extremes of all the class of distance like matrices. If we try to define such a class, then you can think of these two are the extreme cases here. So let me go back to the property that what we want to discuss, the irreducibility. So a matrix M is said to be irreducible if it is not similar to an upper triangular block matrix. That is, if we can find a permutation, if there is no permutation such that it can be written as P transpose an upper triangular block matrix times P, right? So one of the interesting facts why this irreducibility concept plays a good role here is that we know an adjacency matrix or the distance matrices of any connected graph is irreducible. Okay. Whereas it need not hold for the eccentricity matrix. It need not be irreducible. It may be reducible also. Say, for example, if we look at the complete graph, the eccentricity matrix is just nothing but the all ones matrix minus the identity matrix. Right? And in fact, it is also nothing but the adjacency matrix of the complete graph itself. So it is irreducible. Whereas if we look at the complete bipartite graph, okay, so we get this nice block diagonal matrix, which is reducible. Okay. So therefore, we have kind of like, we can pose this question to characterize all the connected graphs whose eccentricity matrix is either reducible or irreducible. And there are some studies, attempts to solve this problem, but of course it's not completely solved. So again, just I've given a formal definition of reducibility here. So now from this definition, we can see that if I want, first thing that I want to make an observation here is that eccentricity matrix is a symmetric matrix. Okay. So claiming that it is irreducible means that we want to look for that it is not similar to a block diagonal matrix. Okay. So in the attempt of solving this problem that was posed, like to identify the class of graphs which gives us an irreducible eccentricity matrix, the first class is the trees. Okay, so if suppose T is any tree of order n, then the eccentricity matrix of T is irreducible. Okay. And this was proved by Wang et al. In 2018 in their recent paper. And by showing this, they also studied some more spectral properties, and they connected the spectrum of adjacency matrix and the eccentricity spectrum of this particular trees. And also they gave some applications in chemical graph theory. So the proof outline, I'm just giving a brief outline because it's in detail and it's like case by case analysis goes in here. So when n equal to 2, we can see that K2 is the only tree and eccentricity matrix is nothing but the adjacency matrix there. And so the theorem trivially holds. And for n greater than or equal to 3, so suppose we assume that the eccentricity matrix is reducible. Okay. Then we can rearrange the vertices in such a way that we can, if it is reducible, then we'll get this block diagonal representation. Right? So where say X and Y are the block diagonal block matrices, where X is of order R and R by R, and Y is n minus R by n minus R. Then picking up any two vertices where there is a non-zero entry in either of the X or Y, we can see that they, let us start from the diametrically opposite pairs of vertices, and we'll show that, first of all, first observation is that since we have either X or Y is non-zero here, any diametrically opposite pair of vertices, diametrically, the pair of vertices which are diametrically farthest, they have to be coming from the same partition. In fact, this X and Y are going to be like, if you rearrange the vertices or relabel the vertices such that X contains all the vertices from the same partition of the tree. And similarly, Y is from the other partition. Then this kind of leads to the fact that say U1 and UN are the two farthest vertices, then they come either from the same, if there are two vertices from which are farthest, then they both come from either X or from Y. Okay. And then we'll arrive at a contradiction by doing a case-by-case analysis by studying all possible non-zero pairs of vertices and show that it cannot happen, that there has to be a vertex from either of the partition, and so that should lead to a non-zero entry, which will give us that the off-diagonal blocks, zero blocks cannot occur here. Okay. So that's a kind of an outline, and this was the first result in irreducibility for trees. So as an extension of this, we can also see that if we have any connected graph on n vertices, and if suppose there is a cut vertex, okay, then if we delete this cut vertex, and if G minus VC contains a component which is a tree, okay, such that the eccentricity of this vertex, I mean, G minus VC is nothing but the degree of, I mean, distance between the vertex VC and any one vertex, any of the vertex from the tree itself. If this happens, then again, ECC is going to be, the eccentricity matrix is going to be irreducible. Okay. And this kind of gave us a lot of insight. And the proof again for this theorem is a detailed case-by-case analysis. So I'll not go into that proof. If anybody is interested, I'll put up the reference at the last. You can look into it. So, but what is our interest? So we are interested in studying the eccentricity spectrum for various graphs. So the first one was for the paths. So as we started with, we start with the path. And if you look at, there is always like two cases occurring because we are studying about eccentricity. When n is even and when n is odd, we'll have two cases arising. So when n is even, the radius is nothing but n by 2. So that kind of gives us the eccentricity matrix is going to have such a representation of block matrices. Okay. Where A is nothing but a matrix, a special matrix of this type, where only the first row, I mean, if you rearrange the vertices in such a fashion, then we can get such a representation of a block matrix. Okay. And this this kind of tells us like we have only the last column and the first and the last rows to be non-zero, and the first column also, yeah. First column, last column, and the first row and the last row are non-zero, and everything else in between will be a zero entry, including the diagonal. Diagonal is also zero here. So again, from this, we can see that if we look at this rank of this matrix, rank is going to be 2. It's very evident that A has the first row, and any one of the remaining rows we can choose for the rank. And all the other rows are dependent rows, right? And therefore, we can see that the rank of this matrix is in itself, it is going to be nothing but rank of this A and A transpose, sum of the ranks of A and A transpose, which is nothing but equal to 4. So whatever be your path, I mean, whatever be the size of the path, the rank of this matrix is going to be just 4. And similarly, for if n is odd, the same argument, except that the central vertex of the odd path leads to a different structure, where this middle row and column, if we see, that is going to be associated with the central vertex of the path. So that kind of looks like this. So again, we have a similar looking structure, except that the entries differ a little bit. And again, we can see that this particular r plus 1th row. So here the first r rows are, the first block is 0. So r plus 1th row and r plus, I mean, taking into consideration my r is nothing but n by 2, right? So we can look into the central vertex and we have this structure, and we can immediately see that the way we have defined over here, it is immediate that r plus 1th row or the r plus 1th column are dependent. Okay, and so deleting this row and column, we can see that we get a block matrix structure which is looking like this. Again, which is similar to the case 1 structure, where we have a block matrix looking similar to the previous case. And again, we can see here that the rank is 4. Right? So this did not only stop with paths, I'll also go in further later. So computing the spectrum, that was what our interest was in. So computing the spectrum, we could just see that the spectrum of Pn had these niceties in them to say where we have gamma 1 minus the difference between the two positive eigenvalues n minus 1, and which is also the same with the two negative eigenvalues. Okay. So, and similarly, we can also see that the largest eigenvalue is nothing but in negative absolute value. If you see, the largest and the smallest are the same. And similarly with the second and the third one, if you look at it in this ordering, whatever I have written over here. So this was looking interesting for us, so we thought we should study more. And similarly for odd case also, we have a similar property with the spectral values. So another extension of this path is like if you add duplicate vertices. So by duplicate vertices, what we mean is a vertex which has the same set. I mean, two vertices are said to be duplicate if they have same neighborhood set. So because those vertices will lead to identical rows in the matrix, in the eccentricity matrix. So we sort of looking into this broom graph. So as you can see, the word broom graph comes from the structure itself, how it looks like. So from a path, add alpha number of vertices to the last but one dependent vertex of the path. So that kind of again will lead to the fact that we'll have n minus alpha plus 1 pendant vertices and one vertex of degree this n minus alpha plus 1. And the remaining vertices are going to be the path vertices which are of degree 2. Okay. So how many ever pendant vertices we add, where as we keep adding, we are not going to alter the rank of this matrix that we get, because each of them are duplicates. Right? So therefore we see that the rank of this broom graph is again 4, and the spectral property is also similar to the path graph because it is kind of constructed from the path. And the characteristic polynomial heavily depends on the characteristic polynomial of the underlying path. So this, and then we also did similar studies on the double broom and other double star-like trees and so on. So, and as I said, we tried to attempt to the conjecture which was given in my abstract, that the eccentricity matrix with the minimal spectral radius was attained by the tree which had one vertex of degree n minus 2. So we were trying to prove that conjecture, but I mean, I shouldn't say but, we proved it and we communicated that work, but by the time somebody else had published that work, exactly in that period, so I don't want to go further into that proof over here. Okay. So let me go into the other aspect where we want to talk about the windmill graphs and the other graphs. So as a generalization, I started looking into this particular product, which is called as the coalescence of graphs. So taking two disjoint graphs, you identify one vertex from both the graphs and join them, glue them together. Okay. So that means what, all the neighbors of both these vertices are now going to be the neighbor of this particular one vertex over here. Right? So this is defined by G1 star G2. So as a simple visualization, you can see that a windmill graph is nothing but coalescence of complete graphs. Or take take n copies of kn plus 1 and glue them all together at one vertex. So that will give you a windmill graph. Okay. Similarly, the Dutch windmill graph is nothing but taking copies of cycle graph and gluing them with a vertex or having a vertex in common with. So I was interested to look into this eccentricity property, the spectral properties of this eccentricity matrix for windmill graph and Dutch windmill graph. That's where we started up, and this work is now accepted or published, going to be published in discrete mathematics. So first, let us see what we can discuss here. So first thing is we want to see whether this the matrix ECC, the eccentricity matrix of this windmill. In fact, we go with the generalized windmill graph over here. There is coalescence of n number of complete graphs, not necessarily complete graphs of same size, okay, or same order. So we went for a very generic case. We started with coalescence of Ka1, Ka2, Kam, where A1, A2, Am are all any integers, okay, greater than or equal to 3. Let's start with a minimal K3. So if we consider this, then the eccentricity matrix of this graph is an irreducible matrix. So how can we prove this? Because the proof is not so immediate, but it does follow through a sequence of process. So let me go through this. First thing is, let us observe that the number of vertices in this graph is going to be sum of all these AIs minus m plus 1, right? So if we look at this matrix, say let me just denote it by small n so that it becomes easy for us to progress. So the eccentricity matrix is again a block matrix here, where the first row is going to represent the central vertex, which is the vertex which is glued together from all these complete graphs. So if we see that vertex has, except at the diagonal entry, all the other entries are 1. And we have another block representation, which is nothing but all ones matrix of size n minus 1 by n minus 1 and remove the diagonal blocks of the size of each of these complete graphs, right? So this is the very nice looking structure where we have like, it's a dense graph with all ones and except the diagonal blocks. So now if we try to show, the main purposes, we want to show that this is irreducible, right? So to show that it is irreducible, I want to go into by looking at the diagonal matrix of this, by where the diagonal matrix is going to represent the sum of the rows of this ECC matrix. Okay. Each row of the diagonal matrix is representing the sum of this sum of the rows of the ECC matrix. So that is again given by the first row is going to be n minus 1. And if we look at the remaining rows, we'll have the diagonal block matrix here, where each entry is given by each of the sub-blocks here will contain the same entry there. Okay. So twice n minus a1 plus 1 is the identity matrix, which is a block matrix of size a1 minus 1 by a1 minus 1. So that we can see right from here that each of the smaller blocks, we are deleting all these entries over here, right, from the n minus 1 entry. So that is what is written over here. N minus 1 times a1 minus 1, so which is combined together here in this form. And so now if we go into a definition which is like a Laplacian, like you take the matrix M and the diagonal matrix, which is nothing but the row sums of the given matrix M. So if you look at this matrix B, we want to use a result over here to show irreducibility, which says that if such a matrix M minus the diagonal matrix which contains the row sum of this matrix M, if that is a full rank matrix, I mean, if it is a rank n minus 1 matrix, okay, then we can immediately say that the original matrix is irreducible. Okay, so this is the property that we'll be using over here. So next we head to show that the rank of this B matrix over here is nothing but n minus 1 is equal to n minus 1. So to see this, first we can observe that this smaller block matrix here, the 2n minus s block, that is again a full rank matrix. And so because it's going to be diagonal, and so the matrix has n minus 1 as the rank. So we can see that at least n minus 1 is the rank of this matrix B. Okay. Now, to see that it is in fact equal to n minus 1, the only left out row is the first row. So we can immediately see that the first row is dependent on the remaining rows. And in fact, how it is dependent is you take the sum of all the remaining n minus 1 rows. And so that is going to be given by this expression. So which is nothing but if you simplify this expression, we see that it is nothing but negative of R1. Okay. So we can immediately see that the matrix is dependent. In fact, I mean, it is singular, and therefore the rank is less than or equal to n minus 1. And therefore we can immediately conclude from the previous observation that the rank is going to be equal to n minus 1. So this, since rank of B is equal to n minus 1, we can immediately conclude from this result that the eccentricity matrix, which is the core matrix for us, that is in fact irreducible. So this kind of gave us a good feeling that the irreducibility is there. So we can kind of, the irreducibility also tells us like we can apply the Perron-Frobenius result. The theory itself can be applicable to these kind of matrices, right? So again, to go into the spectral properties, we wanted to compute the spectrum of coalescence of all these complete graphs. So we start with first two complete graphs to see what is the behavior of this. So if you go into it, for two complete graphs, the eccentricity matrix is given by this block matrices here. And in fact, we can see here that it has a very nice property that the eccentricity energy is twice the spectral radius. Okay. And why it is so, we can see that the spectral radius is nothing but the largest eigenvalue. And since eccentricity matrix has trace 0, we can see that the spectral radius is, the sum of the eigenvalues is going to be obtained from the spectral radius itself, right? So the largest eigenvalue here is, and there is only one positive eigenvalue here, so that kind of connects everything over here. So let me just go into the proof. So again, going into a partitioning of this eccentricity matrix, looking at the partition, it forms an equitable partition, and the corresponding quotient matrix reduces to a 3 by 3 matrix, which is looking like this. And so we can see that again from the quotient matrix, we can use the property of the quotient matrix here. Whatever is the rank of the quotient matrix, we can see that is going to be the rank of the original matrix also. So right from there, we can we obtain that there are only 3 non-zero eigenvalues for the eccentricity matrix, right? And among these 3, there is only one positive eigenvalue, and that kind of leads to the fact that the eigenvalues, if we take the positive sum of all these eigenvalues, then we get the eccentricity energy to be equal to twice the spectral radius. Okay. And I'm not going into these details. These are just my computational work where we can compute, and patiently we can sit and solve these cubic equation. Now extending this from two complete graphs, coalescence of two complete graphs, to higher order. Okay. So we again go into first the simplest case, which is the windmill graph, that is where every complete graph has equal size, okay, or equal number of vertices in them. So excuse me. So again, in this case also, like the previous one, we find that we observe that there is only one positive eigenvalue and 2 negative eigenvalues. And so again, this same result kind of can be extended. The eccentricity energy is nothing but twice the spectral radius, right? So the proof also carries in a similar line, but I'll just show you how the matrices look like, which looks interesting for us to see. So the partitioning of this eccentricity matrix is again forms the equitable partition for windmill graph also, which is given by this matrix here. And in fact, this is again a full rank matrix, which of order m+1. So we can see that the characteristic polynomial of this matrix is again given by this expression, lambda plus 2n to the power of m-1, and with this quadratic polynomial with it. So this quadratic polynomial leads to the one positive and one negative eigenvalue. And from here, we can see that minus 2n is another eigenvalue of multiplicity m-1. So the spectrum is kind of revealed directly from here, but computing the polynomial from the quotient matrix takes a little bit of effort to come to this, to arrive at this point. So now for the bigger case, for the generic, that is coalescence of n number of complete graphs, right? So if we choose A1, A2, AM to be the any integers, and we take the complete graphs of those orders. And if you want to look for the ECC spectrum of this graph, then as before, I mean, this kind of, it can be easily generalized, like whatever we had seen for windmill graph and the when m equal to 2 case, it can be extended to any m. That is, there is always only one positive eigenvalue for this matrix and m negative eigenvalues, m being the number of complete graphs that we take, right? And so this again leads to the fact that since there is only one positive eigenvalue, it leads to the fact that spectral, I mean, eccentricity energy, which is nothing but the sum of the absolute values of the eigenvalues, is twice the spectral radius, right? So again, here I'm not computing the spectrum, but we'll try to show why that n plus is equal to 1, that is number of positive eigenvalues is 1, and why n minus is m. Okay. So again, going back to this eccentricity matrix, the representation I'm just giving here, which we had seen already. So again, looking at the n matrix, this is again, as we remember, this is nothing but J, the all ones matrix minus this, removing the block diagonals of all ones again, right? So this is again a full rank matrix, and so and the rank of this n is nothing but equal to m itself. Okay, m is, I mean, I wouldn't say it's a full rank, I'm sorry. Each block, whatever was removed, we can see that the first set of A1 rows are going to be identical. Similarly, the A2 minus 1 row is going to be identical, and so on. So each of this block gives us one rank, I mean rank equal to 1, and therefore we can see that the rank of this n matrix n is equal to the small m, that is the number of blocks in the matrix, or in the graph itself, we can say the block of complete graphs. So now to see along the first row, along with the first row, here the first row is not dependent, as we can see here. So we get that the rank of this matrix is going to be equal to m plus 1, right? And alternatively, looking at the quotient matrix, the quotient matrix has this representation, which is equal, which is like for each block we'll have the entries coming out to be the size of that matrix. It's A1 minus 1, A2 minus 1, and so on. And this matrix is again an m plus 1 by m plus 1 matrix, and it is of full rank. So now applying interlacing theorem, we'll try to show why our claim holds. Okay. So suppose lambda 1, lambda 2, lambda m plus 1 are the eigenvalues of this quotient matrix M. And since already we have shown that this eccentricity matrix is irreducible, we can immediately see that there is at least one positive eigenvalue, which implies that lambda 1 is at least positive for us. Right? So this much is guaranteed for us. And to show that the remaining, from starting from lambda to all the other eigenvalues are zero, I mean, or negative, you can use now the interlacing theorem and apply induction technique to show this. So for base case m equal to 2, we have already verified it from our previous result for m equal to 2 case. So going further, for m equal to 3, now let us look at this QM matrix and look at the principal submatrix by deleting the last row and last column. So if you see the principal submatrix of this QM, we can immediately see that this is going to represent the quotient matrix of m minus 1 complete blocks, right? That is from the original graph G. If we delete the last complete graph block, then we can see that G prime is nothing but, I mean, the corresponding quotient matrix of G prime is nothing but QM minus 1, because there are only m minus 1 blocks over there, and that would be nothing but equal to the principal submatrix of QM. Right. So just from there, we can see immediately that suppose the eigenvalues of this block matrix is denoted by B1, B2, Bm. And by induction, again, we can see that we'll have this beta 1 to be positive and beta 2 to beta m are negative. And now by interlacing theorem, we can see that lambda 1 is greater than or equal to beta 1 is like greater than or equal to lambda 2 and so on. And so applying interlacing theorem on this principal submatrix, so we can immediately conclude that since beta 2 is negative, we can see that from lambda 3 onwards, all the eigenvalues become negative. That's quite immediate. So just to see that lambda 2 is also negative, we just go into the other properties where trace of the quotient matrix was 0. So that implies some of the eigenvalues is 0 again, right? So putting it back into this expression, we can simply see that lambda 2 can be represented in this way, right? Just from the properties of the eigenvalues, we see that lambda 2 becomes negative, right? And since lambda 2 is a non-zero eigenvalue, it cannot be equal to 0. So therefore, it is strictly less than 0. So this kind of gives us a bigger picture of how the spectral values are for the coalescence of M complete graphs, any M complete graphs. So we are not restricting on the size, other than that it should be at least 2, right? So this and continuing from here, why is it a property of just coalescence of complete graph, or can it be extended to other graphs also? So we entered into this eccentricity property of Dutch windmill graphs, or the coalescence of cycles. So first case we began with was when M equal to when we had 2 complete cycles and looking at their coalescence, or the Dutch windmill graphs, right? So if we label the cycles in this particular fashion, say first case, we have taken the M even case, right? So in this case, suppose we label the vertices in this fashion. That is, V1 is my central vertex, and V2, V3, V4, V5 are the level 1 vertices. And in fact, we can see that if we do a BFS, the breadth first search from V1, we can give a labeling for each level first, complete the levels, and then go along. And for this labeling, okay, we get this matrix representation here. And we can immediately see that this matrix is irreducible. Why? Because if I delete my vertex V1, we can see that we get 2 components which are trees, that is, in fact, they are paths, right? And of course, we will see that the eccentricity of these paths would be nothing but distance between V1, comma V. So using that, we can see that this matrix is irreducible, and we can also see that the special block matrix representation again gives us some nice properties about the spectrum also. Now, for the odd case, there is this minor difference for the odd case, that the block matrix in the previous one was just that the last 2 rows representing the last extreme vertices, the diametrically opposite vertices were involved. Whereas here we'll have 4 vertices which are kind of a pair of vertices where we have from either of the cycles which will be involved in here, right? So that is the only difference that takes place here. Otherwise, the technique is the same, right? So again, the irreducibility is kind of guaranteed here again. So going into the spectral property, we see that the rank of this ECC, this matrix is again 4, like what we had in the path case or the trees case. Most of the trees case we had 4. So similarly here also we get the rank to be equal to 4. And in fact, it has this nice looking representation, which is like kind of about the point value k plus a, k minus a, and minus k plus b minus k minus b are the representations, right? Where a and b are these values in the square root. Right? And similarly, when m is odd case also, we get such a representation, and rank is again 4 here. And so the proof is again just by using the property of the matrix and solving the characteristic polynomial, we get the proof of this, we get this expressions here. So, so this kind of leads to the fact, again, if we see there are, in this case, when there are two complete graphs, we see that there are two positive eigenvalues and two negative eigenvalues. And the number of, the rank is again 4. So all the remaining are zeros are 2m minus 5 are there. Right. So now the question is, can I extend this to n number of cycles and do it for a general coalescence of cycles, general graph, which is the generic form of this coalescence of cycles. So when we look at C3, that is coalescence of 3 cycles, that was a different case. So we get that the characteristic polynomial for the corresponding ECC matrix, okay, was given by this expression, a nice looking expression. So where we see that there is again only one positive eigenvalue here, which is one of the roots of this quadratic expression. And all the others are negative values, which is in fact -4 repeats n minus 1 time, and one more negative root of this expression, and all the others are 0. Right. So here we have, from here we can immediately conclude these things, that n plus, that is, there's only one positive eigenvalue and n negative eigenvalues, and n zeros are there. Again, since there is only one positive eigenvalue, we also find that the energy, eccentricity energy, is twice the spectral radius. But this is not the case when we go for more than 3 cycles, right? So when we take general case, when m is greater than or equal to 4, but fixing m constant. So we take m cycles and just consider the coalescence of m cycles, say n number of m cycles. Okay. When m is odd, when we consider all odd cycles, so we get this to be the polynomial where C1 and where we have again 0 as an eigenvalue, which repeats like which has multiplicity of n times m minus 3 plus 1. And we have a quadratic expression. The roots of this are again one is a positive root and one is a negative root we get. And similarly, we have in between, if you see, this is again a polynomial which is of order 2n minus 2, but it has repeated roots. It is also a quadratic polynomial with multiplicity n minus 1. So there are n minus 1 positive eigenvalues, all are identical, and similarly n minus 1 negative eigenvalues, which are repeated. So similarly, for in the m even case, we again see a similar structure, but the expression, the coefficients just differ by some constant values over here. And so this tells us that from here we can see that there are n positive eigenvalues and n negative eigenvalues, which is similar to the previous discussion that we were doing over here, right? So as we see in n plus k, for taking 2 copies, we had just n plus and n minus to be 2. So it can be extended now for any n copies, as n plus and n minus have become equal to n. So this is what I've been recently, I got inspired for this generic case, of course, from when we wanted to study the general Dutch windmill graphs. So again, there are some more cases left out over here, which looks clumsier in the expression form. So that's why I'm not putting it up over here. So these are some of the references. The first one, this is where most of the results that whatever I had given is getting published. And in the other papers, Randic's paper, where this is where the first place where eccentricity matrix was introduced. And Wang in this 2018 paper, he extended it from Randic, and they worked on a lot of applications to chemical graph theory. Right? And this is the paper where I was talking about that conjecture, and I said I'll talk about tell the status of that conjecture, but I also found that it has been published already, so I'm just giving the reference here so that the conjecture is solved. So I'm not going further into that, in that direction. So with this, let me stop here for any further questions or comments, suggestions.